Einstein's special relativity, introduced in 1905, completely revolutionized our understanding of space and time. It requires that the laws of physics are invariant under Lorentz transformations, and that time and space are relative and treated on equal footing. Einstein's special theory of relativity has been confirmed in many experiments, including the observations of time dilation by different experimental groups. The Schrödinger's wave equation, formulated in 1926, on the other hand, is a fundamental equation describing the subatomic realm. It ushered in the era of quantum mechanics and successfully accounts for the diffraction of electrons, discrete spectra of atomic gases, particularly that of hydrogen, among many others. 2 years later, Paul Dirac successfully obtained a relativistic wave equation, which fully accounts for special relativity in the context of quantum mechanics. In this video, we shall follow Dirac and understand his motivation and lines of reasoning that led him to his famous equation. We will derive the Dirac equation and understand why the bi-spinor are 4 components. Structure of the wavefunction is the minimal dimensionality to obtain a relativistic analog to the quantum wave equation. The Dirac equation also introduced conceptually difficult concepts such as negative energy solutions, the prediction of the positron, and the idea of the Dirac sea. In this video, we will use graphene to unravel some of these difficult concepts through tabletop experiments. You shall be amazed by how some of these esoteric ideas can be understood in very intuitive terms in simple experiments with graphene. A relativistic quantum wave equation. Taking the square root.
But the theoretical physicist is just sitting in an armchair and thinking things over. How can he be led to a discovery? The answer is that he works from the mathematics. He takes the mathematics of the existing theory. There is a formalism, a number of equations which have to be interpreted in a certain way. He studies this formalism and notices an imperfection in it. And then he proceeds to try to remove this imperfection. If he succeeds in doing so, he will be led to some new equations. Then he looks for the physical meaning of these new equations.
Our discussion begins with the Hamiltonian, or the total energy of the system, defined to be the sum of the classical kinetic and potential energies. Quantum mechanics provide a standard prescription of how to obtain the Schrödinger wave equation by simply replacing the dynamical variables energy and momentum with their differential operators in time and spatial coordinates as shown. We then arrived at the well-known Schrödinger wave equation with first-order derivative in time and second-order derivative in space. The Schrödinger equation governs the wave function of a quantum mechanical system, herein denoted by the symbol psi. This can be written more compactly in terms of the Laplacian. Schrödinger equation is the fundamental equation of motion in quantum mechanics, much like Newton's second law in classical mechanics. The Schrödinger equation, however, is not a relativistic theory. In the 1927 Solvay conference, many anticipated that the next big thing in physics would be a quantum wave equation that is compatible with the special theory of relativity. Not surprisingly, the Solvay conference that year is titled Electrons and Photons. Relativistic electrons cannot exceed the speed of photons and must satisfy the Einstein special theory of relativity. We recognize the famous rest mass energy mc square in the square root. Pulling out the mc square factor and performing a Taylor expansion to leading orders in P, we arrived at the following terms. This includes the rest mass energy, the classical kinetic energy P square over 2m, and a relativistic correction of P to the power of 4, and so on. Now, if we use the standard prescription of replacing the dynamical momentum variable with the differential operator, we will end up with an infinite series. Clearly, this does not look like a feasible approach. In 1926, a year before the highly anticipated Solvay conference, Oscar Klein and Walter Gordon proposed a relativistic wave equation. He began by squaring both sides of the equation to remove the square root. Again, using the standard quantum mechanics prescription for the dynamical variables E and P. they arrived at the first relativistic wave equation. Today, the Klein-Gordon equation is known to describe massive spin-zero particles, such as the Higgs boson. However, the Klein-Gordon equation is second-order differential in time, a clear departure from the Schrödinger wave equation, which is first-order differential in time. At that time, Paul Dirac was also working on a relativistic wave equation for quantum mechanics and became aware of Klein-Gordon results. However, he found this to be intolerable. Paul Dirac believes that the general Schrödinger equation, which described the quantum state evolution in first-order differential in time, should not be forsaken. In other words, Dirac is determined to find the relativistic Hamiltonian in this general form of the Schrödinger equation.
I remember very much an incident at the Solvay conference in 1927. During the interval before one of the lectures, Niels Bohr came up to me and asked me, "What are you working on now?" I told him I was trying to get a satisfactory relativistic theory of the electron. Then Bohr answered, "But Klein has already solved that problem." Klein had this equation and this interpretation. Klein and Gordon had worked it out independently. And Bohr considered that as a solution of the problem of getting a relativistic theory of the electron. I started to explain to Bohr that I wasn't satisfied with that and wanted to explain to him why, but just then the next lecture started and our talk was cut short, and I never did get a chance to explain just what my objections were to this theory of Klein. The objection, of course, is that we have a very beautiful and powerful quantum mechanics based on this equation of Schrödinger and the corresponding equation of the Heisenberg theory. It is so beautiful, so powerful, that it seemed to me that it had to be right. I was very much impressed by the power of this theory because I had seen it grow up step by step and had taken a part in it. And then people wanted to scrap all this beauty and power and replace this basic Schrödinger equation by something different, something to which you cannot apply the standard rules of quantum mechanics. And that I found just intolerable.
Thus, Dirac was determined to take the direct square root of this equation. We know from basic algebra that this is only possible if the terms within the square root is a perfect square. Here we write out explicitly the four terms, highlighted in blue. As a warm-up, let's just start with two square terms within the square root. For the terms within the square root to be a perfect square, there must exist some alphas where this equation is satisfied. First, let's take the square on both sides of the equation as shown. Comparing the coefficients of the terms on the left and right, we can arrive at these constraints on the alphas. Their squares must be 1, and their product do not commute. The first condition would suggest alpha is some complex exponential phase, but that would not satisfy the latter as product of numbers surely commutes. Thus, there is only one way out. Alphas has to be matrices. Dirac knew about the Pauli matrices, and that matrices do not necessarily commute. The Pauli matrices was invented by Pauli Wolfgang when trying to describe spin half physics. It is straightforward to check that the square of these Pauli matrices are indeed 1, or the identity matrix. Next, the product of two Pauli matrices yield the next Pauli matrix. For example, sigma 1 times sigma 2 equals I times sigma 3. In fact, their product follows a cyclic symmetry as shown. Thus, the Pauli matrices do not commute, and their commutation relation is as shown here. Now let's return to our original problem and check what happens if we let the alphas be the Pauli matrices. We see that the Pauli matrices indeed respect these two conditions as shown. Thus, we can take the square root of px squared plus py squared, provided they are 2 by 2 matrices as shown. Of course, any two of the Pauli matrices would do the job. Okay, let's up the game and increase the number of squares in the square root to 3. Following the same procedure as before and take the square on both sides, we can arrive at similar constraints for the alphas. Namely, the square of alpha must be 1, and that the product of any two alphas incur a negative sign when their product ordering is switched. These are the same requirement as before, and thus our Pauli matrices should do the job. Thus, we can take the square root of px squared plus py squared plus pz squared. Here it is implicit that these are 2 by 2 diagonal matrices. In this case, we must utilize all the 3 Pauli matrices. The Einstein relativistic energy, however, have 4 squares within the square root. By extension, we can take the square root using similar reasoning. However, we have a problem. Can we find another Pauli matrix, herein denoted as sigma 0? There are only 3 Pauli matrices that satisfy the algebra highlighted in green. The 4th Pauli matrix, herein denoted as sigma 0, does not exist. So what should we do? It doesn't take Dirac long to realize that there is no need to restrict oneself to just 2 by 2 matrices. He proposed a set of 4 by 4 matrices, which satisfy the same algebra as the Pauli matrices. It is straightforward to check that the square of these Dirac matrices are indeed 1, or the identity matrix. Next, the product of 2 Dirac matrices yield the next Dirac matrix with a cyclic symmetry as shown. Thus, the Dirac matrices do not commute, and their commutation relation is as shown here. These are the same algebra as the Pauli matrices. Thus, these 4 Dirac matrices satisfy the required algebra for us to take the square root. In summary, Dirac found that the minimal relativistic analog to the quantum wave equation would require a Hamiltonian that is 4 by 4, which then admits solutions where the wave function is a 4-component vector. Thus, Dirac obtained the Hamiltonian he was looking for, expressed in terms of the 4 by 4 Dirac matrices. Using the standard quantum mechanics prescription for the dynamical variables, he obtained the relativistic wave equation as shown. The Dirac equation reveals a satisfying symmetry between time and spatial coordinates, where both are now first order. Solutions to the Dirac equation. Negative energies in Dirac C. We would like to work out the eigenenergies and eigenfunctions of the Dirac Hamiltonian. Let's write out its 4 by 4 matrix representation explicitly in terms of the gamma matrices as shown. The particle rest energy takes the block diagonal, while the particle kinetic energy takes the off-diagonal blocks. This Hamiltonian can be easily diagonalized with symbolic mathematical tools like Mathematica or MATLAB. Just drop a comment if you want me to send you the script. We consider an electron and plot its eigenenergies as a function of momentum. The magnitude of its energy is as highlighted. Its eigenenergies admit a positive and negative solutions, indicated by the red and blue curves, respectively. These eigenenergies are doubly degenerate. An energy gap appears at the otherwise crossing of these positive and negative solutions of about 0.5 mega-electron volts, which corresponds to the rest mass energy of an electron. Since each eigenenergies are doubly degenerate, they each admit a pair of eigenfunctions, herein denoted by the superscript up and down arrows. These wave functions are 4 components vectors and are also known as bi-spinor, for reasons that will become apparent later. Let's first examine how these wave functions look like when the electron is at rest. For the positive energy states, the first 2 components of the wave function are representation of the up and down spin states. Thus, the first spinor represents the electron's up and down spin states. This result was pleasantly surprising to Dirac, as he did not anticipate to produce a theory for the electron spin. We see that the electron spin is naturally built into the Dirac model. On the other hand, for the negative states, the up and down spin states are represented by the lower spinor. However, what does negative energies mean physically? How should one interpret these negative energy states?
One could suppose that what physicists ordinarily mean by a vacuum is not a region of space where there aren't any electrons. It would be a region of space where all the negative energy states for electrons are occupied. That, in fact, is the most reasonable definition for a vacuum, because you might consider the vacuum to be the state of lowest energy. And putting electrons into negative energy states, you get a negative energy each time you do it. So the state of lowest energy would have all the negative energy states occupied. We get a new picture of the vacuum. Rather disturbing to begin with, but still one can accept it. The vacuum is a sort of sea of negative energy electrons. And then we may have departures from the vacuum in two ways. We may have some electrons lying outside in positive energy states. These would be the ordinary electrons, and they cannot then normally jump into negative energy states because the negative energy states are occupied. However, there might be a hole among the negative energy states, just like a hole in the closed shells of chemical elements. Such a hole will be a region of positive energy because there is a lack of negative energy there. And also, it will behave like a positive charge. So that the hole will appear as a reasonable physical particle with a positive energy and also a positive charge.
Negative energy solutions are unsettling because it would suggest that relativistic particles can decay into infinite well through radiation, which is of course untrue. To overcome this difficulty, Dirac proposed that the vacuum is consisting of bottomless sea of electron occupying the negative energy states. Since electrons are fermions, they must obey the Pauli exclusion principle, which means no two electrons can share the same quantum state. With this redefinition of the vacuum, Dirac can explain why electrons are forbidden from falling into the sea of negative states. However, through radioactive decay or with highly energetic photons, a vacancy in the Dirac sea might arise. A vacancy in the Dirac sea can be viewed as a hole, which is a particle with equal and opposite charge to the electron and has positive energy instead. An electron cannot jump into the negative states unless there is a hole, which then they will annihilate each other and emit high-energy radiation. Thus, what we can observe are only any departures from the vacuum state, which are electrons in positive energy and holes in negative energy states. Electrons and holes have opposite charges and group velocities, allowing them to be distinguished in experiments. In 1932, Carl Anderson studied the tracks of cosmic ray particles in a cloud chamber and discovered a positively charged particle with a mass seemingly equal to that of an electron. With the help of a large electromagnet, he was able to cause the ionizing particles to bend into circular paths. Through the curvature of those tracks, Anderson could calculate the particle's momentum and determine the sign of the charge. Positron was discovered, confirming Dirac's prediction. Making the connection with graphene, a tabletop experiment of Dirac electrons. Graphene is a monolayer of graphite, which is what is used in the lead of a pencil. Graphene is made up of carbon atoms arranged in a honeycomb lattice structure. We illustrate here the honeycomb lattices with black dots and the carbon atoms in big yellow dots. Their lattice vectors are as indicated, and the carbon-to-carbon atom spacing is about 1.4 angstrom. Graphene has two basis atoms in its honeycomb lattice. It is customary to label them as A and B atoms, herein denoted by red and blue, even though they are both carbon atoms. We see that each of the basis atoms form a hexagonal lattice. For example, we have here the hexagonal lattice of the A atoms And here is the hexagonal lattice of the B atoms. Thus, they are also called sublattices. Hence, the honeycomb structure of graphene can be viewed as being made by two hexagonal sublattices from the A and B atoms. We refer you to our videos in the graphene playlists, where we discuss how one can compute the electronic structure of graphene within the tight binding model and how its low-energy Hamiltonian is given by the Dirac model. The Brillouin zone of graphene has a hexagonal shape, where the high symmetry points are located at the zone center and the vertices, herein denoted as gamma and kappa point respectively. There are two inequivalent kappa points, so it is customary to denote them as kappa and kappa prime. Graphene is a semimetal whose conduction and valence bands are linearly dispersing and meet at the kappa point. Due to its linearly dispersive bands, their point of intersection is also known as the Dirac point. The electronic wave functions for each valley are also described by a two-component spinor wave function. Physically, it represents the probability amplitudes at the A and B sublattices. The complete wave functions of electrons in graphene is thus also of the bi-spinor form. Therefore, the low-energy Hamiltonian of graphene is also 4×4. It has a block diagonal form that resembles the relativistic Dirac Hamiltonian, where each block describes the K and K prime valley. Now let's compare this graphene Hamiltonian with that of the Dirac equation for relativistic electrons. First, in graphene, electrons are massless, thus m equals to 0. Second, we must replace the speed of light with the Fermi velocity of electrons in graphene. Third, it is customary to describe electron momentum in terms of its wave vector, and this mapping from P to Q can be done with the de Broglie relation. Lastly, one must perform a unitary transformation to transform the sigma dot momentum block from off-diagonal to diagonal. To sum it up, electrons in graphene mimic massless relativistic particles whose dynamics can be described by the relativistic Dirac equation. In what follows, we shall represent the electronic structure of graphene with respect to the magnitude of Q. The Fermi velocity in graphene is 1 million meters per second, which is 300 times smaller than the speed of light in vacuum. In charge-neutral graphene, the Fermi level is located right at the Dirac point. In the zero temperature limit, all states below the Dirac point will be occupied by electrons as depicted here. In graphene, one can make capacitor structures consisting of a metal gate, oxide layer, and graphene. The application of a gate voltage Vg can then allows one to capacitively induce free carriers in graphene, thus tuning its Fermi level. Such tunability is a clear departure from relativistic electrons in vacuum, thus allowing for the study of Dirac electrons in unprecedented ways. When Vg is 0, the Fermi level is located at the Dirac point, and electrons filled up all negative energy states. We remind you that electrons are fermions and follow the Fermi-Dirac distribution function. At zero temperature, all states below the Fermi level will be occupied, while those above it will be unoccupied. Thus, the electrons filled up all negative energy states. One might ask if this would contradict the charge neutrality condition. The answer is no, because the Dirac C electrons is perfectly balanced by the positively charged lattice ions. Now, what happens when Vg is positive? A positive voltage at the metal would induce electrons in graphene, thus raising its Fermi level into the conduction band, or the positive energy states. When counting the electron density N, we count the number of occupied states in the conduction band only. Thus, only the electrons in the conduction band are contributing to negatively charged excess electrons and is what we want to keep track of. On the other hand, when the Vg is negative, it pushes the Fermi energy into the valence bands, or the negative energy states. This would lead to the depletion of electrons in the negative energy states above the Fermi level. The depleted electrons would lead to new positive charge. We called an unoccupied electronic state in the valence band a hole, and it has the same charge as an electron, but positive. When counting the hole density P, we count the number of unoccupied states in the valence band only. Electrons and holes in graphene can also be detected in the presence of a Lorentz force, much like how positrons was detected by Carl Anderson. One would fabricate Hall bar devices with the application of electric and magnetic field as shown. The Lorentz force will lead to separation of the electron and hole carriers along the direction transversal to the applied electric field. The measured transverse voltage, or what we usually call the Hall voltage, can be used to determine the sign of charge carriers. In fact, the first observation of electron and hole carriers in graphene through the electric field effect has led to the explosion of research in graphene. Let's turn the page to a well-known paradox. In 1929, Oscar Klein obtained a surprising result when he applied the Dirac equation to the familiar problem of electrons scattering off a potential barrier as shown. He found that if the potential energy is at least of the order of the electron rest mass energy, the barrier is nearly transparent. When the barrier energy approaches infinity, the reflection diminishes and the electron can perfectly transmit across the barrier. If Klein's prediction is correct, then electrons within an atom would escape from the nucleus electrostatic potential well through Klein tunneling. We now know that Klein tunneling is impossible in vacuum due to the Pauli blocking by Dirac C electrons. However, the electric field effect control in graphene can make for unprecedented means to investigate the Klein paradox on a tabletop experiment. For example, with electrostatics gates, one can create a graphene electrostatic junction defined by regions with electrons and holes. The former is called N region, while the latter P region. We call such a device a p-n junction. When a lateral electric field is applied across the p-n junction device, the Fermi energy of the two regions are displaced, opening a transport energy window as shown. The current that transport across this p-n junction in graphene has been experimentally measured, and it indeed confirms the phenomenon of Klein tunneling. Now we turn to our last example, that of electron-positron pair production. Patrick Blackett thought that a cosmic particle traveling very fast might have the energy to strike a nucleus and create an electron-positron pair. In the spring of 1933, Patrick demonstrated the existence of showers of positive and negative electrons, both in approximately equal numbers. They confirmed that gamma rays can transform into positrons and electrons, plus a certain amount of kinetic energy, a phenomenon known as pair production. In graphene, such electron-hole pair production can be stimulated through light and can be measured through its photocurrent response. In graphene, where electrons behaves as massless Dirac fermions, electron-hole pairs generation can be stimulated with infrared to visible light as depicted. These laser sources are easily accessible in most optics laboratory. The photo-excited electrons and holes are then separated with the applied electric field. Since their charges are opposite, their contribution to electrical current adds up. Such photogenerated electrons and holes in graphene has indeed been observed experimentally. Dirac did not at first fully appreciate the importance of his results from the union of quantum mechanics and relativity to the eventual discovery of the positron. Indeed, his accomplishment was considered by many to be on par with the works of Newton, Maxwell, and Einstein. A quote from Paul Dirac best summarizes his own achievement. The measure of greatness in a scientific idea is the extent to which it stimulates thought and opens up new lines of research.